Hello everyone. I welcome you all in my next class on Ganit Setu. In my last video, we have recorded about how to multiply two matrices. Right? Today, I will illustrate some more examples on multiplication of matrices. Whenever we study any chapter of 12th, it's always connected and assume that all your previous concepts of class 11th are clear. And in this regard, the most important is trigonometry. All the trigonometrical identities and formulae should always be on your tongue, because whenever you do any question, even on matrices, you will see there are many trigonometrical identities and formulas which are applicable. So I will illustrate two questions here on multiplication of matrices to just give you an idea. It's of NCERT textbooks, and this question has been asked many times in the exam also, CBSE. A matrix A is given here, 0 minus 10 alpha by 2, 10 alpha by 2, 0. And I is the identity matrix of order 2. You have to show that I plus A is equal to I minus A multiplied by cos alpha minus sin alpha and cos alpha. Now you can see that there is this angle is alpha and this is alpha by 2. So you should have relation between angle and half angle. Half angle formula can apply. Or if you can recall the double angle formula, easily you will be able to make this formula. So here it comes how to express sin theta, cos theta all in terms of 10. So you can recall the formula of sin 2 theta. Though there are many formulas sin 2 theta, one is 2 sin theta cos theta. If you write in terms of 10 theta, 2 sin 2 theta is equal to 2 tan theta upon 1 plus tan square theta. And what is cos 2 theta? It is 1 minus tan square theta upon 1 plus tan square theta. If you divide both, you get the formula of tan 2 theta. You can recall it. It's a 2 tan theta upon 1 minus tan square theta. These three identities are applicable here when you convert angle into half angle. So you have to express cos alpha. You can recall that cos alpha will be written as 1 minus tan square alpha by 2 upon 1 plus tan square alpha by 2. Similarly, sin alpha throughout will be written as 2 tan alpha by 2 upon 1 plus tan square alpha by 2. If you will convert double angle into angle alpha, if you take 2 theta equal to alpha, theta will become alpha by 2. These two identities are applicable here. Now to simplify this question, what you can do here, you write this two formulae and then assume 10 alpha by 2 as x. So these two identities we are applying, so better to start from right hand side. It is I minus A, and this two formula taking 10 alpha by 2 as x here, what will be cos alpha? 1 minus x square upon 1 plus x square minus sin alpha. So 2x upon 1 plus x square. Again sin alpha 2x upon 1 plus x square, and cos alpha is 1 minus x square upon 1 plus x square. I think it is clear. What we assume 10 alpha by 2 as x. As a result, now what is I minus A is here? I means 1 0 0 1 minus A means this function 0 minus 10 alpha by 2 means x, 10 alpha by 2 means x, and 0. This is there, right? This matrix remains same as it is. This one here. From entire of this matrix, what you can write here again? 1 minus x square upon 1 plus x square. As it is, you can copy it. Now you can simplify this, subtracting one matrix from another. It's 1 x minus x 1 1 minus 0, 0 minus minus x plus x, 0 minus x minus x, 1 minus 0, 1. Now from entire this matrix, you can see that one common scalar is here, 1 upon 1 plus x square, because x square can never be negative, right? 1 plus x square will never be equal to 0. So this you can take out. 1 upon 1 plus x square is out. Now what is remaining? 1 minus x square minus 2x, 2x and 1 minus x square. This is only remaining. So now as a result it is a scalar which you can write before here, and now to multiply only these two matrices. That is our next step. So if you have any doubt till this step, you can see here. I can recall it for you again. This question is very important whenever it comes in the exam. It's angle alpha and it's alpha by 2. It's a sine cos and it's a tan here. So you should have just recall the formula. This formula should be always on your tongue. Sin alpha 2 tan alpha by 2 upon 1 plus tan square alpha by 2. Cos alpha 1 minus tan square alpha by 2 upon 1 plus tan square alpha by 2. Tan alpha by 2 we took as x here. So this entire expression, the right hand side which we have started, comes up to this form. Now further we simplify. So I will rub these steps here. Now it is the constant scalar I am writing here, 1 upon 1 plus x square out, and these two matrices are here now. 1 x minus x 1 multiplied by 1 minus x square minus 2x, 2x and 1 minus x square. I will drop this. Now you have to simplify this. Simple. The scalar will be always out, multiplied. Multiplying matrices, first row, first column. First element multiplied by first plus second multiplied by second, 2x square. First row, second column. 1 into minus 2x, it's a minus 2x. X multiplied by this gives you x into 1 minus x square. Now starting with second row, first column. First row entry by first and second by second. So 1 multiplied by 2x. Now again, second row, second column. Minus x minus 2x gives you 2x square plus 1 multiplied by 1 minus x square. Two x square minus x square, it's x square. X, then it is 2x square minus 2x minus x cube. So x minus 2x is minus x cube. We are taking minus x common. So what it will be? 1 plus x square. 2x minus x, it's x plus x cube, x common. It's again 1 plus x square. And it's a 2x square minus x square plus 1 plus x square. Simple. Now from this matrix you can see 1 plus x square is out. So when you take 1 plus x square out, already it is 1 plus x square here in the denominator, 1 minus x, x and 1, this get cancelled. So this is how we come to right hand side. Now come to left hand side here. I will drop this now portion which you have done. So this was our right hand side, I minus a. We replace cos alpha sin alpha using that formula identity here, and x means tan alpha by 2. We simplified the bracket, multiplied this 2, is the resulting here. Now come to the left hand side part. The left hand side is here, I plus a, simple. I means 1 0, 0 1 2 by 2 identity matrix, plus a is means 0 minus x, x 0. Add both, it's 1 minus x, x 1, which is same here as equation number 1. This is first, this is second. So from first and second, we can easily verify that left hand side is same as right hand side. If you have any doubt, you ask. Rest of the questions you can easily try, right? So this was about multiplication of on matrices, right? Now next today we'll discuss is about the transpose of a matrix and its properties. So for the next topic we'll discussing in the same is transpose of a matrix and its property. Transpose of a matrix. Suppose A is a matrix. Its a transpose is denoted as either A dash or you can write A to the power T. We call it transpose of a matrix. To obtain the transpose of a matrix, you have to convert rows into columns. Simply get the transpose. For example, if I have here A11, A12, A21, A22, and you find it's a transpose. So transpose means converting rows into columns or interchanging them. Simple. So first row will become first column, second row will become second column. This becomes a transpose. Now, for example, if I take a matrix A here as 2 1 0 minus 1 3 4, and if I find it's a transpose, so converting rows into columns, the first row becomes first column, second row becomes second column. If I transpose it again, then first row becomes first column, second row second column, third row third column. It's again same as matrix A. So this gives us the first property of transpose, that the transpose of a matrix, and again finding double transpose is same as the matrix itself. So finding the transpose means converting rows into columns, simple. And you find the transpose of that again, you find the same matrix. So it's called double transpose, right? Now we discuss another properties of transpose. Easily you can see without verification that if you are multiplying a scalar by a matrix and find it's a transpose, scalar will be out. It's only transpose of a matrix, nothing to verify about this, right? The another property is the transpose of sum or difference is same as sum or difference of the transposes. This is the second property. This also you can easily verify. Means you first add two matrices and then find the transpose, or you first find the transposes separately and then add them. The result is same. But the next property is another important property, that says transpose of AB is same as transpose of B into transpose of A. Here order matters. Whenever you multiply the matrices and find the transpose, the order matters here. Transpose of AB is not same as transpose of A into transpose of B, but it is same as transpose of B into transpose of A. And this can be asked to verify in the exam, maybe in short answer type questions, like maybe in 2 marks type questions. So one illustrating the example here. For example, if you are given a matrix A here, 2 minus 1 3, and suppose B is a matrix here. Now what is the order of matrix A here? 1 row 3 column. What is here? 3 rows 2 columns. So AB is possible. First AB should be possible, because if AB is possible then only this property can be verified. So here yes, it's possible. Let's try it. So we have to verify here that transpose of AB same as transpose of B into transpose of A. This you have to verify, and to verify it, first you find the product of A and B. So what will be the resulting order? 1 by 2 means 1 row and 2 column, that's all. So we take first row first column, right? So taking first row first column, corresponding entries will multiply and add. 2 multiplied by 0 0, plus minus 1 multiplied by minus 1 minus 1, plus 3 4 is 12. Then comes first row and second column, that's all. So 2 into minus 1, it's a minus 2, plus minus 1 into 3 is minus 3, plus 3 2s are 6, that's all. This is the result. So 12 minus 1 is 11, 6 minus 5, 6 minus 5 is 1. This is a AB, right? Now finding the transpose of AB. What it is? 11 1. To convert row into column. This is the left hand side, okay? So I hope left hand side is clear. So I write here left hand side value. That transpose of AB is 11 1. Now you will go for the right hand side. So I will rub this portion. What we did, we multiplied A by B, we got AB, and then we took its a transpose, converted rows into columns. Simple. Now for the right hand side. We are going for right hand side now. The right hand side says transpose of B multiplied by transpose of A. So B transpose, converting first column into first row here, second column into second row. Interchanging rows into column, you get transpose. Transpose of A, this is a column matrix, it becomes row matrix now, and row matrix becomes column matrix. So the row becomes column. Now what is the order here? 2 rows, 3 column. Here 3 rows, 1 column. Right. So again, multiplication is possible, and the resulting will be of order 2 by 1. That means there will be 2 rows and 1 column, same as of left hand side. So let's try. We start first row, first column, you will get first element. 0 into 2, it's 0, plus 1 into minus 1, minus 1, plus 4 3 is 12. And then second row, first column now, because there is no other column. So minus 1 into 2, it's a minus 2, plus 3 into minus 1, minus 3, plus 2 3 is 6. So it's a 12 minus 1, 11, 6 minus 5 is 1. This is the right hand side, and this is the left hand side. You can see both are same. So from first and second, what we conclude, that left hand side is equal to right hand side. So this way we have verified this property. The transpose of AB is same as transpose of B into transpose of A. So these were the properties of transposes. Thus we have seen today all the properties of transposes. Let's recall them. Double transpose is the matrix itself. If we multiply scalar and finding the transpose is same as scalar is out, it's a transpose. Sum and difference of two matrices and then finding the transpose is same as first find the transposes and then add or subtract them. But whenever you find the multiplication, the order changes. Right. Now, on the basis of transpose, we defined the types of matrices, and there are two types of the matrices we will discuss here: symmetric and skew-symmetric. Whenever you say that transpose of a matrix is the matrix itself, it's called symmetric. But if you find the transpose of a matrix and if it is same as negative of A, it's called skew-symmetric. Can you think of any example? For example, if you are taking here an identity matrix 1001 or 1002 also you can take. Now find its transpose, converting first row into first column and second row into second column. It remains same as A again. So it is an example of a symmetric matrix. Right. How can you take the example of skew-symmetric? Means if you find the transpose and you get minus outside. If you find it's a transpose here, let's see what you get. First row becomes first column, second row becomes second column. But if you take minus out, now from this it's 0, minus 1, 1, 0. So it is negative of A. So this is an example of skew symmetric matrix. So whenever you see the transpose of a matrix is same as the matrix itself, it's an example of a symmetric matrix. But in case when you find the transpose of any matrix, and if you observe that each of its entries gets multiplied by -1 like here, right? Or you can say the transpose of a matrix is negative of a matrix, then it's called skew symmetric matrix. Now we see some important result and conclusions based on these properties and types of matrices. These results are very important for you to understand. If you add a transpose of a matrix to the matrix itself, this resulting is always a symmetric matrix. That means, but it is possible only for a square matrix whenever A is a square matrix. So, whenever think symmetric and skew symmetric types are defined only for a square matrix only, because if you say the transpose of matrix is equal to matrix, or even if you say transpose of matrix is negative of matrix, in both the cases order should be equal. Then only they can be compared. That means it is only defined for a square matrix. So these are the two types of square matrices, you can say a symmetric matrix and a skew symmetric. So any square matrix, if you find it's a transpose, and if you say that it is equal to matrix itself, it is symmetric, and if transpose of a square matrix is negative of matrix, then it's a skew symmetric. This is very important result. If you add any square matrix with its transpose, the resulting is always a symmetric matrix. This helps us to design an example of symmetric matrix. This is you can design. If whenever somebody asks you to give an example of symmetric matrix, you think of any square matrix, and add to its transpose to it. You will get the resulting always a symmetric matrix. How? Let's take P here for example. Now to prove that its resulting is always a symmetric matrix, let's find its transpose. So we know that transpose of sum is same as sum of the transposes. And double transpose is the matrix itself. So A plus B same as B plus A, commutative property is applicable here. So what you get? P dash is equal to P. What it shows that P is a symmetric matrix. Right. So whenever you add transpose of a square matrix to the square matrix, the resulting will always be a example of a symmetric matrix. A result is clear. But on the other side, another interesting result you derive here. If you subtract transpose of any matrix from a matrix, the resulting is always a skew symmetric matrix. So whenever you have to give an example of a skew symmetric matrix, consider or imagine any square matrix with entries real or complex and subtract it from its transpose. So resulting will always be a skew symmetric matrix. This is you can imagine on a given example. Now, how to code the skew symmetric? Let's say find its transpose now. So when you find the transpose will be separated. And double transpose is the matrix itself. Now we write it as a matrix, so minus is out. It is equal to minus q. So what do you see? That transpose of q is equal to negative of q. What it proves that q is a skew symmetric matrix. So that means what is the result now? That A plus transpose of A is always a symmetric matrix. A minus transpose of A is always a skew symmetric matrix. And with the help of this result, what we conclude? If you add both, that means P plus Q, the result is 2A. right? This is symmetric and this is symmetric matrix. If you add both, what you are getting? 2a. So that means if you remove this 2 from the right hand side, it becomes half. This is the most important result. What we conclude here, that every square matrix can be expressed as a sum of a symmetric and a symmetric matrix. Every square matrix can always be expressed as a sum of a symmetric and a symmetric matrix. A can be any square matrix. You can imagine of order 2 by 2 or 3 by 3. Find its transpose, subtract and add. So when you add and half it right outside, it's P here. Assume it to be P here and subtract transpose of A from A and multiply by half its cube. Add both P and Q, resulting will always be A. This proves that every square matrix can be written as a sum of a symmetric and a symmetric matrix. I will illustrate one example. For example, this question is very often being asked in the examination. If they can ask any square matrix, say of order 3 by 3. Express this matrix as a sum of a symmetric and a symmetric matrix. So you will assume let it be A here. Find its transpose. Second row, second column, third row, third column. You get its transpose. Directly you design now matrix P here, which is half A plus transpose of A. That means add both and keep half outside. Okay, so adding both 2 plus 2, 4. Corresponding integers minus 1 plus 1, 0. 0 minus 2 is minus 2. Second row corresponding integers 1 minus 1, 0. 3 plus 3, 6. 0 minus 4 minus 3 is 1. Now third row minus 2 plus 0 minus 2. Minus 3 plus 4, 1. 1 plus 1 it's 2 here. You got it P? Now you have to show that it's a symmetric matrix. So here only you can find it's a transpose. Now finding its transpose here, transpose of P. So it's half out. Take its write this P here and find its transpose. So convert rows into column. First row into first column 4 0 minus 2. Second row second column 0 6 1. Third row third column minus 2 1 2. And you see that it's the same as P only. This proves that P is a symmetric matrix. Now we have seen that P is a symmetric matrix, right? I will write the value of P here on the side. We have got matrix P as here of 4 0 minus 2 0 6 1 minus 2 1. Now what you do, you have to find out Q. So I will get Q. Q is half A minus transpose of A. That's all. Subtract transpose of A from A corresponding it is 2 minus 2 0 minus 1 minus 1 it's minus 2 0 minus minus plus 2. Second row from second row corresponding integers, right? It's 1 minus minus plus 1 1 plus 1 it's 2 here. Then 3 minus 3 0 4 minus minus plus 3 is 7, right? Now minus 2 minus 0 it's minus 2 only, minus 3 minus 4 minus 7 1 minus 1 0. This is Q here. Now when you find it's a transpose here, convert rows into columns. First row becomes first column, second row becomes second column, third row becomes third column. But you see that all these entries now got multiplied by minus 1, so we take minus out. And you see that their sign changes. minus out है ना, तो -2, -7 and 0. It's the same as -q. We have taken minus out from each of these entries. So what you have seen, that transpose of q is equal to minus of q. What it proves? That q is skew symmetric. So we have what q also now. Q is equal to half minus half, and q is equal to half 0 minus 2 2 0 7 minus 2 minus 7 0. So these are the steps here. First you find A is given. Now I find transpose of A. 8 both multiply by half and get P here. And this you have to show that P is symmetric. Means you have to prove transpose of P is P. Then form Q. Q means subtract transpose of A from A, multiply by half. You got Q, take its transpose. You observe that it is equal to negative of Q. This proves that Q is skew symmetric. Write Q here and finally rotate P and Q both to get A. So now we add P and Q both. Adding means half is out. Corresponding integer 8 now. Now you have to divide down. You have something is wrong here. No, -2 plus 2 is 0. No? We have added P and Q both. You can check the corresponding integer. No? 4 plus 0, 0 minus plus -2 is -2. -2 plus 2 0. So corresponding, now each of these entries is divided by 2 here. Here 1 minus 7, it comes -6. And 2 plus 0 comes 2 here. Dividing it by 2 here, it is -3 and 1, which is same as A here. And it will be A. If there is anything comes wrong, you can check. There are mere chances, but it should not be any silly mistake at all. So this question is many times being asked in the exam, and so this result is very important. That every square matrix can be expressed always as sum of a symmetric and a skew symmetric matrix. So I hope today's class is complete, and it was complete detail about transpose of a matrix. You can practice varieties of the questions from NCERT textbooks, take the exercises on multiplication, solve each and every examples first, which are given already there solved, and then try and solve the questions. Similarly, in based on transpose, solve the entire exercise of NCERT textbooks and the questions, examples also based on this. Apart of this, at the same time, you should try the questions given in NCERT exemplar. Right? You can go, and even if you want, you can download. It is available easily on an NCERT exemplar. And there are hot questions in exemplar. Many times in CBSE nowadays they are asking hot questions from exemplar. So try to attempt all the solved and unsolved questions of exemplar as well, based on the same concept. So I hope today's class is fruitful for all of you. Have a great day.